Hi everyone, and welcome to our lesson on projectile motion and specifically how to apply the motion equations to projectiles. So with these problems, you usually assume you have some kind of ball or particle launched at a certain velocity, and I'll draw the velocities in yellow here, from some point. So I've got A point in time, here B is another point in time, and C is another point in time. And when you apply these motions equations, you assume that the projectile is in the ideal conditions, which is in a vacuum. Therefore, they only have one force on them, and that force is in green, the gravity force. So I'll draw that in here. There's the gravity force, and there's the velocity. Now, when the ball is at its max height, it has zero vertical component to its velocity, but it is still moving sideways. And you can verify this by chucking your pencil or a little rubber across the room. You'll find that the velocity at the top is purely horizontal. And then as it comes down to land, or it comes down to the same level at which you threw it, its velocity will look like that. And since this is under ideal conditions, the force acting on the particle does not change. And that gives us our constant acceleration, which enables all these formulae over here to work. So the force on the object is the same. We'll call this the ball. In order to understand how our motion equations work for projectiles, we have to divide up the velocity into both horizontal and vertical components. I'll draw the horizontal component in red and the vertical components in purple. So here we go. Here's the horizontal component of the velocity for the ball at this stage. The arrow extends just so it falls on the line beneath the yellow velocity line. Here's the horizontal velocity at B. It matches up perfectly with the absolute velocity. And here it is at C. So it stops on this vertical line. Now here is the vertical component to the velocity. I sometimes draw the arrow here, but I think it's actually better to draw it acting from the center of the object. There we go. There is the vertical component of the velocity at point A. Here's the absolute velocity. Here's the horizontal component. Here's the vertical component. At B, there is no vertical component to the velocity, so we don't draw it. And again at C, it's this arrow here, but I'll draw it from the center of the object, acting down there. So the big thing you should notice straight away is that although the direction of the yellow arrow is changing, and the yellow arrow is here, it's obscured, I'll draw it again. The direction of the yellow arrow is changing, and its size is changing. However, the horizontal velocity component is identical at both A, B, and C points in time. The vertical velocity component is changing. It starts off with a positive value, it goes down to 0, and then it becomes negative. Since the vertical component of the velocity is changing, there must be a force acting on this ball, and the force is gravity. Since gravity is acting in the same direction as the vertical component of the velocity, it is able to change it, but since it is acting at right angles to the horizontal component, gravity does not change the horizontal component of the velocity. Let's look at how we can apply this to a problem. So say we have a projectile, and it's being launched at velocity. I'll keep drawing velocity in yellow. Velocity 250 meters per second. So we'll say it's a cannonball, and that is happening at 30 degrees to the horizontal. Since we are under ideal conditions, we have just one force, the force of gravity there, which seeks to accelerate that cannonball down at 10 meters per second squared. Or we're going to say A equals negative 10 meters per second squared. Under non-ideal conditions, we'd have a second force in green here, air resistance, but we're going to ignore that since it is ideal conditions. We want to figure out a few things. Number one, what is the time to reach max height? Number two, what is max height in terms of displacement. Number 3, the time of flight. And number 4, the horizontal distance achieved. So horizontal displacement. So we'll make a few assumptions to begin with. Number 1, we'll say the ground extends this way, so when the ball lands, it'll land on the same level to as it was launched. So let's focus on the time it takes to reach max height. First of all, as we did up here, we need to find the horizontal and the vertical components to this velocity. Now, we used trigonometry in the video on projectile motion to prove that the vertical component to this velocity here, so I'll separate this out, we'll say vertical, and over here horizontal. The vertical component of a velocity acting at 30 degrees to the horizontal, where the velocity is 250 meters per second, is equal to, so vertical velocity components, 250 sine 30 degrees, since the vertical component is opposite to the angle. And this is equal to 125 meters per second. We can say there is a big division between vertical and horizontal, so from now on we're only going to consider VV as simply V. So the initial velocity is 125 meters per second, and we can say that is U. That's the symbol we use in our formulas up here, but you can equally use V naught. So the time to reach max height. Let's put in a few things we know. We know that the acceleration is equal to negative 10 meters per second squared, since all objects feeling the force of gravity and no other force will accelerate down at 10 meters a second squared. The initial velocity in a vertical direction is 125 meters per second. And if we're talking about the max height, well, an object reaches max height here, where the vertical velocity component is 0. So we have 3 variables, and we're trying to find the 4th one. Let's look for a formula up here that has A, U, and V in it, and we're trying to find T. It's this one here. There's A, there's U, there's V, which we know, therefore we can find T. So being good physics students, we try and get T by itself. So we have V equals U, I'll do this in blue, actually yellow. V equals U plus AT. We try and get T by itself. V take away U on A equals T. Therefore, T equals V is 0, U is 125, so negative 125, and A is negative 10. Negative 125 on 10 equals 12.5. That is the time it takes for this cannonball to reach its maximum height, or the time it takes for gravity to completely nullify the vertical component of the velocity. So let's look at part 2. What is the max height? There are a few formulas we can use. We could use this one because we know U, we know V, and we've worked out T. But if there's one tip I can give, it's that this answer for T we have comes from our own equations. We may be mistaken in this working here, so it's usually safer to use the knowns that you're given or that are closest to what you're given. In this case, we know that the final velocity has to be 0 at max height. We know that the initial velocity here was 125, that's a pretty sure bet. And we know the acceleration for sure. We don't have to involve time, which we've worked out here, although the equation may seem easier. So let's try and use this equation down here. So number 2, S. We're trying to get S by itself here. V squared equals U squared plus 2AS. V squared take U squared on 2A equals s. So that should be our max height there, that s value. And this is equal to, well, at max height v equals 0, so that's 0. U squared equals 125 squared. And 2a is 2 times negative 10. And in the calculator this comes out to 781 meters. So that indicates that the cannonball is able to rise up to a height of 781 meters from the height at which it was launched. Now number 3, the time of flight. We can exploit the symmetry of this example. Since the ball lands over here at the same height at which it was launched, it will take the same amount of time going up as it does going down. Therefore, we can say the total time of flight, t, is equal to 2 times the time it took to go up, which was 12.5. Therefore, the total time of flight is 25 seconds. And finally, we can use this bit of information to figure out the horizontal displacement. So finally, we look over at the horizontal section. The horizontal velocity, VH, is equal to cos 30 multiplied by 250, which comes to around 217 meters per second. This horizontal velocity does not change. Therefore, if we want to find out how far this cannonball actually travelled, we know that v equals u and acceleration equals 0. That's just saying the initial velocity equals the final velocity. So the distance travelled, d, is equal to v multiplied by t, which is sort of, where is it? It's practically this formula here. If you let s equal d and you let a equal 0, you just have d equals ut. So, or in this case vt, since v equals u. D equals vt. Distance equals v, 217 meters per second, multiplied by 25. That comes to around 5.43 times 10 to the 3 meters, or 5.43 kilometers, which is quite a range. If you don't have any air resistance, things traveling at high speed tend to go for a very long way indeed. Now, the final thing they might ask, this is a bit of a challenge question. What is the speed at landing? Let's figure that out. So if the total flight time is 25 seconds, let's figure out the vertical component of the velocity over here, which is the little purple arrow. V equals u plus at. Therefore, the final velocity equals, started off with, 125. And then we have plus negative 10, 25. So the final velocity vertically is negative 125. The final horizontal velocity, since the horizontal velocity does not change, is equal to 217. So we have this vector here. We have the ball landing. It's got a vertical component of negative 125. It's got a horizontal component of 217. And we want to know what is the resultant velocity given by that yellow arrow. Well, we can use Pythagoras. V squared, that yellow, is given by 217 squared plus negative 125 squared. Therefore, V is equal to the square root of 217 squared plus 125 squared. Actually, it's plus negative 125 squared. That doesn't make a difference though. And V is equal to 250 meters per second, which is the same in magnitude to the velocity up here. Now, if the ball does sail through the air, reach a max height and land over here, you expect that all the gravitational potential energy you've gained falling from here to here no, how do I say this? The total amount of energy of the system cannot have changed. Over here it has 0 gravitational potential energy and a lot of kinetic energy. When it reaches the max height there, it has a lot of gravitational potential energy but slightly less kinetic energy because this yellow arrow is actually shrunk. And when it lands again, it again has 0 gravitational potential energy, so you suppose that all the energy is again in kinetic, which means it has to have the same overall speed as when it was launched, and we do find that to be the case. So these motion formulas, they preserve energy and they agree with the other parts of physics. The really important things to remember are, the first step is to separate the velocity into its horizontal and vertical components. After you've done that, the focus is usually on the vertical component, because that will tell you the time of flight, or the time it takes to reach certain heights. And it is often that the final thing you do is apply the time of flight to the horizontal velocity. And just remember, the force of gravity only affects the vertical component of the velocity, not the horizontal component.